One. So what we're going to be talking about today is ionic and covalent bonds. So ionic versus covalent. We've talked a little bit about both these and how they act as bonds and what are some of the differences between them. And just so you guys know, right now on the projector you see the whole screen, but what's going to actually be in the video is just what's inside this dotted box, okay? So, ionic versus covalent. The first one we're going to talk about is ionic bonds and the compounds that form them. So, ionic compounds have a very special name. So, because they're always formed from a metal and a nonmetal or a polyatomic cation, we always refer to them as ionic salts, right? So, another term for referring to these ionic compounds are ionic salts. And you always have to have a metal, or typically a metal and a nonmetal. But what it does always have to be is it has to be a cation and an anion. So if you remember, a cation is anything that is going to lose electrons. So they become positively charged because their number of charges, they have less negative charges than positive charges, so now they're overall positively charged. An anion is going to gain electrons. So they're going to have an overall negative charge because they have more negatives than positives. An example of that, if we just look at sodium real quick, sodium has 11 protons and 11 electrons. Sodium is in group 1A, so it wants to lose one electron to be stable. So it drops down from 10 electrons or 11 electrons to just 10 electrons. So now overall it has 10 negative charges and 11 positive charges, which gives it an overall charge of 1 positive. That's where we're getting those charges for the cations and anions from. Now, in ionic bonds, one of the examples we're going to look at here right now is if I say sodium plus chlorine, all right? Sodium is going to lose an electron. It's going to be 1 positive because it's going to give up an electron here. And then chlorine is going to become 1 negative. Because it's in group 7A or group 17, it only needs to gain that 1 electron to be stable. So this electron right here from sodium is actually going to wander its way over to chlorine. Right? So both of these elements become stable because of that electron that was transferred between them. And that last term there is super important because ionic bonds, right, involve the transfer of electrons. And that's really what sets them apart from covalent bonds because electrons are transferred in between them. And we can also see this if we look at our Lewis dot structures. So remember, a Lewis dot structure is whenever we have our element and then the number of valence electrons around it. Sodium only has 1 valence electron, so it gets 1 dot. Chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons, but it has this little gap right here. Remember, they can hold up to 8 when they're happy in their valence shell. So that's why this little electron can just mosey its way on over here, and then both of them are happy because sodium drops back down to its previous energy level and it's stable. And I'm going to pause. Hold on, don't say anything yet. He's Juan in a million. All right. So next one we're going to talk about here are covalent compounds. These are not anything special. They're not called salts. They're just called molecules because they have more than one atom in them. These covalent compounds include our diatomics. We're going to look at a bunch of cool little handy tricks for them. And one of the very different things that separates covalent compounds from ionic compounds is that they share electrons. Right? We share electrons in covalent compounds. So in ionic compounds, it's a very dog-eat-dog world. It's I've got an electron, well, I want to take an electron. Well, I'm giving this one up. You got to move them from place to place. Whereas in covalent compounds, they're all just kind of like, hey, you want to just share electrons? That way it'll be a little bit easier so we can both be stable. And it works a lot better for them. With these, what we're going to do is we're going to look at a couple of examples for them. Just to make sure I got everything so far. Oh yeah. In covalent compounds, it is nonmetals only. Nonmetals only. It is a metal-hating club. Non-metals only. We're going to put a star there. Now, an example of this, and we're going to look at a diatomic one because it's easiest to see if you look at an actual example of what's going on. So we're going to look at a diatomic element, O2. Actually, let's not start with that one. Let's start with H2. All right? This is the diatomic element hydrogen. So in nature, hydrogen is actually found as H2, not as just H by itself, because it's going to bond to another hydrogen to be stable. And this is how that happens. So if we look at hydrogen on the periodic table, it's in group 1A, which means when we look at its valence shell, it only has a single electron, right? If there's another hydrogen next to him over here, this hydrogen is also just a single electron. And what can happen is this hydrogen can just have as one little electron. It's like, hey, I've got an electron, you've got an electron. Why don't we just, share electrons and just put them in between the middle of us, and then they can both be happy. So what happens is we end up with what is drawn like this. This is hydrogen with what is called a single bond between them, right? Because they're both sharing that set of electrons instead of just keeping them for each other. So then this right here is a pair of electrons. It's a bond pair, right? There are two electrons here, and they count for both atoms. So when we're counting the number of valence electrons for each atom, we use that bond pair and we count it towards each of them. So right now, this hydrogen right here has 2 valence electrons from that bond. But this hydrogen over here also has 2 valence electrons because of that bond. So both of them can have a full valence shell where they're happy just from those electrons that each of them brought and shared together. All right? So this one example I have right here, this is what is called a single bond. All right, there's only one bond pair, and there are 2 electrons shared. Now we can take that and move it up a step, because for the next examples, I'm just going to show diatomics here because they're a little bit easier. All right? Oh no, there we go. We're going to look at, did I move too far? Raise your hand, don't say anything. We all good? Okay. We're going to look at oxygen. So O2 is a diatomic. Remember, diatomic means 2 atoms. Diatomic. Di means 2. Atomic means we're talking about atoms. Which is true when we look at our diatomic one. We have 2 atoms here. Now, O2, if we look at them, each oxygen has 1, 2, 3, 4, 5, 6 valence electrons. This oxygen over here has 1, 2, 3, 4, 5, 6 valence electrons. Now, between the 2 of them, they can be like, hey, I've got this electron right here, I want to share it with you, and they share these 2 together, and they've got, oh, we got 2 more, share these 2 together. Then we have 2 more bonding pairs that once again count towards both of our oxygen atoms. So if we count, we have 2, 4, 6, 8 valence electrons for this oxygen, so 8 valence electrons. And checkity check, check, it is happy and stable. And then we look over at this one, it has 2, 4, 6, 8 valence electrons, and it is also happy and stable. So the only difference between, and I should probably label this a little better, this right here, this is our single bond. It kind of makes sense because there is a single bond in between them. This example right here is a double bond. All right? We have 2 bond pairs and 4 electrons being shared. Boop, 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 boop. Done. It's a double bond. And gonna pause real quick. Record. All right. Ladies and gentlemen, we're back. No, I'm just kidding. So next one we're going to talk about here, we're going to look at an example with nitrogen into 2 nitrogens. All right, once again, still a diatomic. So if we put our nitrogens, there's a nitrogen there. We have 1, 2, 3, 4, 5 valence electrons. 1, 2, 3, 4, 5 valence electrons. Now, between these, remember, any electrons that are not paired are the ones that can form a bond pair. So this over here is called a lone pair. All right, this lone pair is going to be special later when we're talking about Vesper because that lone pair is not really available for sharing. It doesn't have to. It's already kind of paired to another electron. It's okay the way it is. When we look over here, This is just a single electron by itself. This electron is what can be shared across with another single electron. And then if we look, nitrogen has 3 of those lone electrons like that, so it can form 3 different bonds. Now, with this is called a triple bond because there are 3 bonds. Triple bond. All right, 3 bond pairs with a total of 6 electrons being shared. Uno momento. And come on. Shh. Don't say anything yet. Now, if we look at this, what this compound looks like bonded now, we end up with in with a triple bond in the middle, in with 2 dots for a lone pair on each side. And I forgot to redraw oxygen up here. Oxygen would be ... double bond oxygen ... All right. So this is a triple bond. There are 3 bonding pairs, 6 electrons being shared between them. All right. And those are the 3 different types. The important part is drawing the Lewis dots between them with the lone pairs and the bonding pairs. You also need to remember that a bonding pair represents for each bond, right? Remember, each bond or each bar is 2 electrons being shared. All right. So right now, this nitrogen, this one right here, has 2, 4, 6, 8 valence electrons. This nitrogen has 2, 4, 6, 8 valence electrons, and that's why they form a stable compound. All right. The last thing we're going to talk about real quick before we do some practice problems on our own is Vesper theory. V-S, brain fart, E-P-R. And it is a theory. All right, and what this stands for is valence shell, shell, electron pair repulsion theory. And what the whole point of this specific one is it tells us about the fact that lone pairs and bond pairs affect the shape of a molecule. Right? And the reason for this is electrons are kind of like people. So if we look at, for example, oxygen, or not oxygen, H2O. So we have H, O, H. Oxygen is going to have 2 lone pairs on it. What this actually looks like in a real world situation, we end up drawing it more like this. H, O, H, and then lone pair, lone pair. Because what happens is these bonding areas, as well as the lone pairs here, are all electrons. And electrons are negatively charged. Now, like charges repel each other, and that's super important to remember. And you can remember the same idea that if you had a room filled with a bunch of grumpy people. So if you had a bunch of me's in a room, that guy's eyebrows going through his eye, no wonder he's so grumpy. If we had a bunch of grumpy people in a room, they're not going to want to all center up in the center of the room and just cuddle up next to each other, right? That'd be weird. They're all going to try and separate. They don't really want to be close to each other because they're all just a bunch of grumpy people. Same thing happens with these electrons. The electrons are all extremely negative, so they're going to try and separate apart from each other and push out as far as they can. So what we end up with is this lone pair is going to actually repel or repulse the other lone pair. They're going to kind of push up against each other and try and separate out as much as possible. So we actually use what is called Vesper theory, right, that valence shell electron pair repulsion theory, to help us determine the actual shapes of molecules. Because water forms something like this, which is what is called a bent shape, whereas it's not going to form a straight linear shape like this, right? That's something we're not going to talk about till tomorrow. So that is it. If I can pause before someone says a word, don't say it.